Assalamu alaikum, dear students. Today is our 27th lecture of Discrete Structures CSC 102. In the previous lecture we had started pigeonhole principle and we were discussing some examples of pigeonhole principle. Today we shall continue that topic and we shall finish that topic first, and then we shall discuss some other counting rules, and I shall give you some introduction to probability. In the previous lecture, as you know, we had discussed counting rules, difference rule and inclusion exclusion rule, and we have discussed pigeonhole principle. The generalized pigeonhole principle we had not discussed due to the shortage of time. Today we shall first discuss it, and then we shall discuss counting elements of disjoint sets and counting the number of integers, a relation between permutations and combinations, and I shall give you a brief we shall discuss some basic topics of probability also. So we were discussing pigeonhole principle. What is pigeonhole principle? Basically, as by definition, we had discussed that we cannot define a 1-1 function from a set to a smaller set. This is what pigeonhole principle says. That is, if you have 5 pigeons and 5 pigeonholes or cages for 5 pigeons, then at least 2 you must close, or you must put in one pigeonhole. So this is what pigeonhole principle is. Now we consider another example of pigeonhole principle, in which selecting a pair of integers with a certain sum. We are given a set A in which we have integers 1, 2, 3, 4, 5, 6, 7 and 8. In the first part of this example, if 5 integers are selected from A, we select any 5 integers from this set, must at least one pair of the integers have a sum of 9. So this is what we have to calculate, we have to investigate, that if we select any 5 integers from A, then is this necessary that at least one pair out of these 5 integers give us the sum as 9. And we shall solve this problem by using pigeonhole principle. First, we have calculated, or we have partitioned the set A systematically, so that in the first subset of this set A we put 1 and 8, the first and last integer. In the second set we put second and second last, third and third last, and fourth and fifth element. This is how we divided this set into a partition, that is, into subsets which are mutually disjoint sets, means any two subsets have empty intersection. So partition the set A into the following 4 disjoint subsets. Now observe that each of the integers in A occurs in exactly one of the 4 subsets, and that sum of the integers in each subset is 9. Thus, if 5 integers from A are chosen, then by the pigeonhole principle 2 must be from the same subset. If you choose any 5, for example the first 5, 1, 2, 3, 4, 5, then 1 belongs to first set, 2 belongs to second set, 3 belongs to third set, 4 and 5 belongs to the same fourth set. Now the pair 4, 5, which is in the same set, has the sum 9. That is, we have 5 integers and 4 subsets. the domain set has 5 elements, and codomain set have 4 elements. So by using pigeonhole principle, 2 must belongs to the same set, and if the 2 belongs to same set, for example 4 5, then the sum of 4 5 is 9. So the answer to the first part A is yes, that is there must be at least one pair of integers which have sum of 9. Now in the B part, if 4 integers are selected from A, must at least one pair of the integers have a sum of 9? Then obviously no, because in the domain set you have 4 elements, in the codomain set you have 4 elements, that is 4 subsets of A. Now if you choose 4 elements in set A, then each element can belong to different subset, so their sum may not be 9. So this is basically a picture of the first part. In this we have 5 elements and 4 sets, so it is necessary that 2 of these 5 elements must belong to the same subset. In the B part, the answer is no. You can see this is the case where the pigeonhole principle doesn't apply. We cannot apply because the domain set contains 4 elements, codomain set contains 4 elements. So the domain set here doesn't contain more elements than the codomain set, therefore we cannot apply here pigeonhole principle, because in pigeonhole principle the domain set must be larger than the codomain set. So this was another application or example of the pigeonhole principle. Now we see what is the generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if k is less than n divided by m, then there is some y belongs to the codomain set y, such that y is image of at least k plus 1 distinct elements of x. Here obviously m must be greater than n. If n is less than n, then k is basically some decimal number, and this there must be some problem. So here it is obvious that n is greater than m. So in generalized whole principle, we define a function from set x to y, and the set x contains n elements, y set contains m elements, and there must be at least one element in the set codomain set y. It is any y, it could be any element, such that it is the image of k plus 1 elements in the set x. So this is what the pigeonhole principle. For example, show how the generalized pigeonhole principle implies that in a group of 85 people, at least 4 must have the same last initial. So in the set x, you have 84 people, means you have 85 persons, 1 2 3 up to so on, up to 84 and 85. So in the second set y, you have initials. Last initials means the last alphabet of their names. For example, my name is Amir Rashid, and D is the last initial, D Amir. For example, my name is Amir, and the last initial of the last alphabet of my name is R. So similarly, we have to see the last alphabet of these 85 people. What are the possibilities? What could be the last initial? It could be A, it could be B, C, D, E, F, G, H, I up to Z. So the last initial could be any alphabet among the 26 alphabets. So the code domain set must be here A, B, C, D up to so on Y and Z. So here we have 26 elements and here we have 85 elements. Now by using, and we have to apply the generalized pigeonhole principle, and we have to show that at least 4 must have same last initials, means that there must be some initial here, for example C, whose pre-image must be at least 4. That is, at least 4 people exist whose last initials in the name must be same. So how this we can apply the generalized whole principle as first of all we divide n by m, that is number of elements in the first set by the number of elements in the second set. So we divide 85 by 26. What it gives us, this is something 3.27 approximately. So now there must be some integer k which is less than this 85 by 26. So the integer which is less than this is 3, because this division gives us 3 point something. So the integer which is less than 3.27 is obviously 3. So by using pigeonhole principle, this k exists, and pigeonhole principle says that there must be some number y, some element y in y, such that y has at least is the image of this y pre-image, or you can say that y is the image of at least k plus 1 distinct elements of x. Here what is k? K is here basically 3. So by using pigeonhole principle we can say that k plus 1, basically 3 plus 1 is the 4 element. K with 3 plus 1 is 4. So by using generalized pigeonhole principle we can say that there must be at least 4 people whose last initials are same. So this is how we can apply generalized pigeonhole principle. So graphically, or we can draw an arrow diagram, as we have constructed the arrow diagrams in functions and relations, and we can obviously see that there must be at least 4 elements here which have same image. For example, this x2, x3, x4 and x19, x anything, it have same initials. So this is what we can apply generalized pigeonhole principle to calculate, to approximate, to evaluate, to solve such type of problems. Next is basically we shall discuss here, in the previous lecture we have discussed combinations and permutations. In this lecture or here we shall discuss what is basically the difference between permutations and combinations. Permutation, you know that it's basically the ordered selection or ordered arrangement of elements, and the combination is an unordered combinations or arrangements of the elements of a set. I repeat here the definitions of combinations and permutations, and then we shall discuss what is the difference between combination and permutation, and then what is the relation between combinations and permutations. As you know by the previous lectures, if we are given 2 non-negative integers n and r, and r is basically less than or equal to n, then R combination of a set of n elements is a subset of R of n elements, and it is denoted by NR, or I have told you that it can also be denoted by NCR, and read as n choose R denotes the number of subsets of size R that can be chosen from a set of n elements, and its formula for computing how we can calculate such possible subsets by using this formula n choose R, or as this we can denote it by NCR. This is n factorial over R factorial into n minus R factorial, and we have discussed several examples of for computing such type of calculations. Now, as an example, I repeat here, I give another example here to remind you what is basically combination. Combination is basically, let S be the set of 4 people, and Bob said, and then we had discussed this example when we had discussed combinations. And we have to form a committee consisting of 3 of the 4 people in S is a 3 combination of S. List all such 3 combinations of S. What is 4C3? So all possible committees which we can form out of these 4 persons is basically the combination. And what are all possible committees which contain 3 out of these 4 peoples is basically combination, means all possible subsets which contains 3 elements out of 4 elements of S. So in the first committee we leave n, we construct Bob, Sid and Dan, and then n, Sid, Dan, n, Bob, Dan, and n, Bob, Sid. So these are 4 committees we can form which contains 3 people out of the given 4 people in the S. This is basically the combination. You can say also that all possible subsets of S which contains 3 elements. This is what the combination, and we can calculate number of these committees by using the combination formula, and we have to calculate this 4C3 or 4 choose 3, and 4 choose 3 is basically by using this formula we can calculate 4 choose 3 by 4 factorial divided by 3 factorial into 4 minus 3 whole factorial. This is 4 factorial. We can expand it like this: 4 into 3 into 2 into 1, and 3 factorial as 3 into 2 into 1, and 4 minus 3 is 1 factorial. This is 1. So this is cancelled out with this, and we get what? We get 4. So there are 4 possible committees which can we make by using 3 people out of these 4 people, or we can say that 3 combination of S. So these are all 4 committees we can form by using 3 people. So this is what the combination is. Now, what is the permutation, and what is an unordered selection? For example, there are 2 distinct methods that can be used to select R objects from a set of n elements. There are 2. Now we shall discuss what is the difference between permutation and combination. Basically, selecting elements out of some number of elements, basically there are 2 methods. One is combination, one is permutation. Combination is basically an unordered selection in which order doesn't matter, and permutation, the order does matter. Similar, that's why we can say combination is basically an unordered selection. In here we can write Bob at the end, Dan at the first, or Sid at the first, Bob at the end. The order of these people doesn't matter. In combination, order of the elements doesn't matter in the combination. For example, in combination the set Dan, Bob or Sid, this set is equivalent or same as this set. We have changed the orders here, then we have put at the first position, Bob at the second, and this Sid at the third position. Now in combination the order is not important, that's why this is called unordered selection. But in permutation order is important. For example, if we have to choose R objects out of n objects, if we have to choose R objects out of n objects, then there are two distinct methods. One is the ordered selection, one is unordered selection. And if we have to choose R objects in an ordered selection out of n elements, this is called basically R permutation. And if we have to choose an unordered selection, order is not necessary there, then this is basically called R combination. Now we discuss this further to differentiate between these two selections. For example, here I have given you an example of the combination in which we have to select 3 elements out of any 3 elements out of 4 elements in which the order is not necessary. Then we can form 4 such type of selections. Now again another example of combination of unordered selection. How many unordered selection of 2 elements can be made from the set this? How many unordered selection of 2 elements can be made from this set? Unordered selection means combinations. We have to choose 2 elements out of 4 elements, so this 4C2 or 4 choose 2 is basically 4 factorial over 2 factorial into 4 minus 2 factorial. This is, I have used here combination. This is 4 into 3 into 2 into 1, and this is denominator 2 into 1 into 2 into 1. So 2 cancel, 2 2s are 4 3s are 6. So there are 6 unordered selections of 2 elements out of these 4 elements. So we can choose it as 0 1 0 2 0 3 1 2 1 3 2 3. Now here the order is not necessary. 1 0 1 is equivalent to 1 0, means this set is equal to this set. Order is not necessary. Here also 0 2 is equal to 2 0. Order is, because order is not necessary. So such type of selection is called basically unordered selection. And now we move to the ordered selection. Write all 2 permutations of the set 0 1 2 3. Find an equation relating the number of 2 permutations P42 and the number of 2 combinations 4C2, and solve this equation for 4C2. Now the number of 2 permutations of the set this is basically P42, which is equal to 12. How? Because we have to, P42 is what? This is 4 factorial over 2 factorial. 4 minus 2 is 2. So this is basically 4 into 3 into 2 into 1 over 2 into 1, 2 into 1, 2 into 1. Cancel, 4 3s are 12. So there must be 12 ordered selection of 2 elements out of 4 elements, where the order is important. If the order is not important, then 4C2 is 6. If the order is important, then 4P2 is 12. Now how to construct 2 permutations of that is the permutations of 2 elements out of these 4 elements. So there is a process of we can use the combinations, the selection of combinations, and then we order those selections to get the number of permutations which is required. For example, in the previous example, these were the 6 unordered selection of 2 elements out of 4 elements. Now if we arrange these selections by considering the order, this will give us the 2 permutations. For example, here the first step is choose a subset of 2 elements from this. Choose all possible subsets of 2 elements out of these 4 elements, as we have done in the combinations. These are the 6 possible subsets which contains 2 elements out of the 4 elements 0, 1, 2, 3. Now in these subsets, choose an order for the 2 element subset. Now we choose the order. For example, here write the 2 combinations of this. The 2 combinations of this basically 6, which are 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3, as we have written here. These are all the possible subsets which contains 2 elements of this set. Now we write them with respect to the order. We write them as 0, 1, we write them as 1, 0. Now here the order is important, because both these subsets will be included in the 2 permutations, because here we have 0, 1, here we have 1, 0. The order is now changed, the order of elements has been changed. So this is important. So these are basically 2 subsets. If in this set we have 0, 2, we write the subset of 0, 2 and 2, 0. So the order has been changed. Similarly, 0, 3, 3, 0, 1, 2, 2, 1, 1, 3, 2, 3, 1, 2, 3 and 3, 2. So the permutations basically they have been doubled. Here in this case, this is not always the case. So here you can see that there are 12, 2, 4, 6, 8, 10, 12. Here there are 12 permutations and there are 6 combinations. So this is basically the difference between permutations and combination. Permutation is basically an ordered selection, and combination is basically an unordered selection of R elements out of N elements. So I hope you understand the permutation and combination. CNR or NCR, basically what is the relationship between the permutation and combination. There is a theorem which shows the relationship between these two, the formulas or the combination and permutation. The number of subsets of R size or R combination that can be chosen from a set of n elements, NCR or N choose R, is given by the formula. N choose R is basically permutation of NR divided by R factorial. As you know that permutation of P of NR is basically what? N P N R is N factorial over N minus R factorial. And you know that N choose R, the first N factorial over R factorial into N minus R whole factorial. So this is basically what? This is PNR. So we can write it as PNR divided by R factorial, or equivalently this. So this is basically the relationship between the permutations and combinations. This is how we can derive the formula for combination using permutations. Now, how to calculate the number of teams? There is an example which shows you where we can apply these combinations and permutations. Consider a problem of choosing 5 members from a group of 12 to work as a team on a special project. So we have to select 5 members, any of the 5 members out of 12 people, how many distinct 5% teams can be chosen? How many distinct 5% teams can be chosen? So we have to choose 5% teams in which the order is not necessary, because here in the question it is not mentioned that we have to follow some order in the selection of team. So therefore there is no order. So we have to calculate the possible distinct 5% teams which can be chosen out of 12, group of 12. So the number of distinct 5% teams is the same as the number of subsets of size 4. That is, we shall calculate what are the possible subsets of these subsets which contains at least 5 elements out of these 12 elements. So we have to use here combinations. So 12 choose 5 is basically 12 factorial over 5 factorial into 12 minus 5 factorial, and we have to calculate, we have to simplify this, and we can calculate that 792 are the possible distinct 5% teams. Now here, what is basically distinct 5% teams? Distinct, two sets are distinct if all their elements are not same. If at least one of the elements in any two sets is not same, then we can say that these two sets are distinct. Whereas the disjoint sets means that their intersection is empty. That is, if we have two sets A, 1, 2, 3, and B is 2, 3, 4, then these two sets are distinct because at least one element, this and this, are not common in these two sets, are not same. So these sets are not equal. That is, they are not equal means they are distinct. But A intersection B is not empty. So these two sets are not disjoint. Disjoint sets are those sets whose intersection is empty. So this is, you have to remember here what is the difference between distinct and disjoint sets. So we can choose 792 distinct 5% teams out of 12 persons. This is how we can apply the combinations to solve such type of problems. Next, how to select teams with members of two types. We have to if in a group of 12 people, the 5 are men and 7 are women, then in total there are 12 people. Now we have to choose teams in some different types, in first part, how many 5% teams can be chosen that consist of 3 men and 2 women? So how to choose such type of teams? So first, this type of problems we shall tackle by using this process. The step 1 is choose the men, choose women. So what are the possible ways we can choose 3 men out of, how many are the men? 5 men. How many are the women? 7 women. So we have to choose 3 men and 2 women. 3 men out of 5 men and 2 women out of 7 women. So 5C3, here again the order is not important. We don't have to care about the order of the men, that is, this man should come here, this man should come at the second place. No, the order is not important. Again, we shall use here to calculate the number of possibilities here by using combinations. So there are 5C3 or 5 choose 3 ways to choose the 3 men out of 5 men, and 7 choose 2 or 7C3 ways to choose the 2 women out of the 7. Hence, by using the product rule, Number of teams of 5 that contain 3 men and 2 women is basically the product of these two. 5 choose 3 and 5 choose 2. So we simplify it and we get that 210 teams can be selected in which there must be 3 men and 2 women. Any of 2 women out of 7, any of 3 men out of 5 men. Now in second part, how many 5-person teams contain at least 1 man? At least 1 man. How we can tackle this problem? This is basically number of teams with at least 1 man. Basically it's total number of teams of 5, which we had calculated here, 12C5, 792. Now at least 1 man, we have to subtract the number of teams of 5 that do not contain any men, which is 7C5, because these are the number of possible teams which contains all women, 5 out of 7, and these are the teams which contains any 5. So when we subtract this from this, we can get the number of teams which has at least 1 man. So we can see this by in another way, that is teams which contain 1 man is basically 5C1, 7C4, because if 1 is man, 4 must be the woman. The teams which contain 2 men are basically 5C2 and 7C3. These, if we simplify this, we get 350. The teams with 3 men is 5C3 and 7C2. So 2, if 3 are men, 2 must be women. Similarly, we can calculate this: teams with 4 men, 5C4, 7C1, and teams with 5 men, 5C5 and 7C0, which is 1 team. So if we add up all these numbers, we get the same number as we have obtained here. So we can calculate it by another way, using this way. So this is how we can use permutations and combinations in daily life problems and in the problems which arises in computer science to calculate the number of teams, number of integers, number of multiples, and such type of problems. Now we start probability. What is probability? Basically, probability is number of, basically percentage, or you can say that what are the chances. Probability, you can say chances. For example, if you have seen cricket matches, before cricket match they toss a coin, and on a coin there is a head on one side and there is a tail on the other side. Now what are the possibilities? Either head comes or tail comes. Now before tossing, what is the probability? What are the chances of winning a toss for one captain? If there are 2 captains, for example 1 and 2nd, now before tossing, what are the chances for one captain to win a toss? How we tackle, how we deal with such type of problems in which chances are involved. For example, another example, you have played in your childhood Ludo game, in which you have thrown several times a die. Die is basically is that which is that thing on which you have seen is written 1, 2, 3, 4, 5, 6 when you throw a die. So what are chances, what are your chances to get a 6 on that die? So such type of problems we deal in the probability, and I shall explain you probability with the help of such type of examples. So before starting probability, we have to define some examples, some basic definitions. For example, the first definition is a definition of sample space. What is the sample space? A sample space is a set of all possible outcomes of a random process or experiment. What is random process? Basically, when you throw a die, the outcome could be 1, 2, 3, 4, 5, 6, because on a die there are only 6 possibilities. So one time it could the outcome could be 2, the other time outcome could be 5, outcome could be 3, 1, 6, anything. So such type of process in which you cannot tell the outcome is basically called a random process or an experiment. And if you do an experiment, for example, you throw a die, you throw it 100 times, what are the all possible outcomes? Means on a die it can appear 1, 2, 3, 4, 5 or 6. No other number can appear on a die. So the all possible outcomes of the die is basically the sample space, that is the sample space of this experiment. That is, you throw a die for 100 times, 200 times, the sample space would be 1, 2, 3, 4, 5, 6. So this is your sample space. And what is an event? An event is a subset of a sample space. An event is a subset of that sample space. For example, if you throw a die, the sample space is A is equal to, for example, A is the set which contains all possible outcomes of throwing that die. That this is basically sample space, and it is usually denoted by S. So we denote it by S. Here, 1, 2, 3, 4, 5, 6. So this is a sample space for the experiment of throwing a die. And what is the sample space for throwing a coin? Is basically S is equal to head, tail. There are only 2 possible outcomes when you throw a coin. Either it comes head or it appears tail on that coin. So now event is basically any subset of that sample space. It could be denoted by any letter, capital letter A, B, C. So 2, 4 is basically an event. That is, when you throw 2 times a die, it appears 2 one time, and the other time it appears 4 on that die. So this is basically an event. So the next definition is equally likely probability formula. If S is a finite sample space in which all outcomes are equally likely. So what does it mean here, equally likely? Equally likely means the chances to appear an outcome is equal for all possible outcomes of that experiment. Means when you throw a coin, what are the chances of appearing an head on that coin? The chances are 1 out of 2. 1 out of 2 means how many chances are there? Either head comes or tail comes. So there are 2 chances. So what are the chances of H to appear on that die is basically 1 by 2. And what are the chances to appear tail on that die is 1 by 2. That is 50-50%. In the simple language, you can say what are the chances that head comes on that die is 50% chance, and the 50% chances are off for the tail. Similarly, what are the chances to appear 6 on that die when you throw a die is basically 1 out of 6. The total chances are 6, and the chances of appearing 6 on that die is 1 out of 6. What are the chances of appearing 5 on that die is also again 1 by 6. What are the chances to appear 4 on that die is 1 out of 6. As the chances of the occurrence of each sample point in this experiment is same. Here 50% of coming head, of coming tail is 50%. Here of coming 1 2 3 4 5 6 on that die is the chances of appearing any digit on that die is equally likely. This is equally likely, that is their chances are same of all outcomes. So such type of experiment or random processes are called basically equally likely. So if S is the finite sample space and E is an event in S, then the probability of E, denoted P of E, capital P of capital E, is basically the number of outcomes in E divided by the number of outcomes in S. If we denote N of A by the number of elements in A, then we can write this formula as N of E divided by N of S. So this is basically equally likely probability formula. For example, we had discussed a typical pin example when we had discussed the permutation, combinations and multiplication rule. A typical PIN P personal identification number is a sequence of any 4 symbols chosen from 26 letters in the alphabet and the 10 digits with repetition allowed. If all pins are equally likely, means their chances to appear are same. What is the probability that a pin chosen at random contains no repeated symbol? So there are basically 141370 pins with no repeated symbol. You can see this number. How we can obtain this number, we have discussed this in the previous lecture. By watching some previous lectures, 25th and 26th lecture, you can understand how we can write this number 141370 pins with no repeated symbol, and there are this number of pins in the total. So thus the probability that a pin chosen at random contains no repeated symbol is this number divided by this number, which is this. That is, in other words, we can say that if we multiply this by 100, we can obtain the percentage. Approximately 84% of the pins have no repeated symbols. These are the chances, basically 0.84, 84% chances that we get a pin who have no repeated symbol. Another example, if the letters of the word computer are randomly arranged in a row, they are randomly arranged, what is the probability that the letter CO remains next to each other in order as a unit? And we have calculated, we have discussed this example in the previous lecture also, 25th and 26th lecture. You can see those lectures and particularly these examples to understand the numbers which are involved here. When the letters are arranged randomly in a row, the total number of arrangement is this. We have calculated this in that example, and the number of arrangements with letters CO next to each other is basically this number, 5040. Now we have to calculate the probability that the letter CO remains next to each other is basically this number divided by this number, which is 1 by 8, and this is 12.5%. Basically 12%, there are 12.5% chances that the CO number remains next to each other if the letters of the word computer are randomly arranged in a row. So this is how we can use the equally likely probability formula to calculate the number of the chances of the occurrence of an event. Next is probability axioms. Let S be a sample space of probability function P from the set of all elements in S. If we have a function P from the set of all elements, all events in S to the set of real numbers, satisfy the following three axioms. For all events A and B in S, the probability of any event must be greater than or equal to 0 or less than or equal to 1, because here in the formula of the probability, equally likely probability, the number of outcomes in E divided by total number of outcomes in S. This E set basically is always a subset of S. Now the number of elements in E must be less than or equal to number of elements in S. So it means that number of elements in E divided by number of elements in S, this must be less than or equal to 1. Equality comes here if E is improper subset of S, that is E contains as many elements in S, then for example E contains 4 elements and S contains 4 elements, then 4 divided by 4, this must be this is 1. If E contains less elements than S, then for example E have 3 elements, then 3 by 4, this must be less than 1, and this probability must be greater than or equal to 0. Why? So E could be empty here. If E is empty, then according to this formula we have 0 divided by number of elements in S, for example 4, then 0 out of 4 is 0. So this 0 is possible to come as a probability, but this probability cannot be less than 0, because this probability formula is basically the number of elements in E and number of elements in S. It depends on this. Now E could be empty, but S cannot be empty, and these are basically finite sets, and in finite sets the number of elements is basically a positive integer, and if we divide two integers which are either 0 or 0 only in the numerator and divided by a positive integer, we cannot get a number which is less than 0. So here we can conclude that the probability of any event which is subset of the sample space must be greater than or equal to 0 and less than or equal to 1. So this is the first axiom of the probability. 2 is probability of empty set. I have told you that this must be 0. If the event is empty, then it contains 0 elements, and divided by if the S set contains n elements, then it is 0. So probability of the empty set is always 0, and probability of S, if we take E equal to S, the event equal to S, then number of element in S divided by number of elements in S, this must be same, so we get 1. So P of S is always 1. So this is basically the second axiom of the probability. If A and B are disjoint means they're empty, their intersection is empty, and distinct means they are not equal. That is, if intersection of A and B is empty, then probability of union of A and B is basically P of A union B is equal to P of A plus P of B. This is the third axiom of the probability. Now we take a simple example to see what is basically how we can interpret these axioms of the probability. suppose that A and B are events in a sample space S. If A and B are disjoint, could P of A is equal to 0.6 and P of B is equal to 0.8? Is this possible? No. Probability axiom 3 would imply here P of A union B is basically P of A, P of B is equal to this equal to 1.4. Now A union B is an event. A union B is an event. We suppose this is E. Now probability of E is equal to probability of A union B, which is 1.4. And we have discussed here that probability of any event must be greater than or equal to 0, less than or equal to 1. But this probability is greater than or equal to 1. Greater than 1, not equal to 1. This is simply greater than 1. So this is not possible. So we can say that these probabilities are not possible. So this is how we can use the axiom of probability to draw the conclusions. Now the probability of the complement of an event. If A is any event in a sample space S, then probability of A complement is equal to probability of 1 minus probability of A. Means if you have A is a subset of S, then probability of A, for example it is 0.3. Then A complement is also basically subset of S, and probability of A complement is basically 1 minus probability of A, because A and A complement is basically, these two sets are disjoint sets. A and A complement, basically they are disjoint sets, and probability of you can say that and probability of A union A complement is basically S. This is also, if A is subset of S, A complement is a subset of S. Their intersection is phi, their union must be S. Now by using the axiom of probability, we can say that probability of A union A complement, this is basically probability of A plus probability of A complement. Now what is this? This is basically S, probability of S. Now we have to calculate probability of A complement. The probability of A, we have same. Probability of S, it comes 1, because as we have discussed here, probability of S is 1. Here we have probability of A, and here we have probability of A complement. Now this goes there, and we can take this on the other side. 1 minus P of A is equal to probability of A complement. So this is how we can write that probability of a complement of a set is equal to 1 minus probability of that set. So for today it's enough. Until the next lecture, Allah Hafiz.